Welcome to a 5-part series on value-centered decision-making. This is the first of 5 lectures in this series. The 5 lectures are going to first focus on value theory. And this is the question of how do we trade off attributes of alternatives when the attributes are certain. For example, we get a job offer at a salary and a certain number of weeks vacation. If we take the job, we get that. There's no uncertainty. There's still a trade-off, though. The second lecture in value-centered thinking focuses on utility theory. And now we're going to introduce uncertainty and risk. And this lecture focuses on uncertainty about money and how we can take into account people's risk attitudes about money. The third lecture, multi-stakeholder, multi-attribute alternatives. Now we look at alternatives that have multiple uncertain attributes, and there are multiple decision makers. The fourth lecture, we look at types of uncertainty and how we can do contingent decision making, how we can allocate the uncertainty so that we don't have to actually address all of it at once. And the final lecture looks at behavioral economics and decision support, and how do we actually support real people making real decisions, and when is it good to trust intuition, and when are more formal methods the right choice. So value-centered thinking, utility theory, again, trade-offs under uncertainty. Basic formulation. We'll do some application to aircraft manufacturing and to a project within the Army Corps of Engineers. And we'll do a lot of discussion, have a lot of discussion about the forms of a value function and how they can be justified, what assumptions are necessary to use these different forms. Then we move on to utility theory, and we deal with uncertainty. And we talk a lot about how executives think about uncertainty, what questions they have. We'll have a brief primer on probability basics, and then talk about the value of information and the whole notion of utility functions and how you can assess them. The third lecture now, we're getting more complicated. We look at multi-attribute utility theory, and we have multiple stakeholders. We again go through a process looking at the issue of what form the function should take. We'll consider some various problems associated, like Arrow's impossibility theorem, where you actually have no surefire mechanism to solve the problem. And we'll talk about a product that was developed to actually allow this overall assessment in a very user-friendly way. Then the fourth lecture, we're going to focus on uncertainties and contingent decision-making, and we're mainly going to focus on investment decision-making, how companies make decisions to invest in either getting better at what they're already doing or investing in new things, new products, new services. We'll look at the types of uncertainties, and there are quite a range of them that affect these kinds of projects. We'll then do real options as opposed to financial options and focus on the issue of how do you attach value to a multi-stage decision process, and then review 14 investment case studies that have been conducted with a wide range of companies and government agencies over the years. In our fifth lecture, we're going to look at how people actually make decisions and look at behavioral economics, the psychological traps that affect people, the heuristics and biases that creep in. We'll talk about a whole range of descriptive models, both from economics and psychology, and then the whole notion of when is expertise and intuition the right thing to use versus when should you use formal methods. We'll also look a bit at how organizations make decisions, not individuals, and some of the problems they run into. You're going to meet some interesting people in these 5 lectures. You're going to meet 5 Nobel Prize winning economists, 5 founders of utility theory, and 5 contemporary thinkers. And I want to introduce them to you now. On the Nobel Prize side, we're going to talk about Kenneth Arrow's impossibility theorem. We're going to talk about Herbert Simon and satisficing and how people make decisions. Robert Merton and Myron Scholes, we're going to talk about option pricing models that they developed along with Fisher Black, who died before the award. And then finally, we're going to talk about Daniel Kahneman, who got his Nobel Prize for behavioral economics. The founders of utility theory will be also people you'll meet. Thomas Bayes, Daniel Bernoulli, and Jeremy Bentham, back in the 1700s, worried a lot about the whole notion of utility and what is something worth to somebody. In the 20th century, John von Neumann and Oscar Morgenstern formalized this. In their famous book in 1948 on theory of games and economic behavior, they formalized utility theory, gave it a firm mathematical basis that you'll learn about in lectures 2 and 3. You'll also meet several contemporary thinkers. Ralph Keeney and Howard Rafa wrote the book Decisions with Multiple Objectives, which was a book actually used with this course often, and Real Choices, which is a more pragmatic day-to-day kind of guide. Gary Klein has done seminal work on the whole notion of expertise and intuition, and when you can actually pay attention to your expertise and not worry about formal methods like we've discussed in these lectures, and when should you actually pay attention to these methods. Henry Mitzberg is famous for his paper on the folklore of management decision-making and the whole notion that managers are cool-headed analytical optimizers, and how that is not true, and that's not how day-to-day life actually works in any kind of reasonable organization. And then Malcolm Gladwell is the popularizer of several interesting books, Blink, Tipping Points, and Outliers. And these books have popularized some of the material, for example, from Gary Klein's work. And you'll get to meet these people in the course of these lectures. So value-centered decision-making covers a range of ways of thinking about value, thinking about attributes, how they trade off, how to handle uncertainty, how to stage decisions in order to manage uncertainty, how to deal with multiple decision makers, how to balance intuition and expertise versus formal methods. And that's what this 5 lecture series is about. So let's get started. Today we're going to talk about how to attach value to alternative investments, to alternative choices, and how to balance multiple attributes that relate to that value. Today is value theory, while next lecture is going to be utility theory. Value theory is concerned with certainty, where basically once you pick an alternative, what you get is what you expected. When we get to utility theory, we're going to be concerned with choosing alternatives where there's uncertainty associated with the consequences of choosing the alternative. But today we're not going to worry about that. We're going to start off with a basic formulation of this trade-off under certainty, looking at risks, returns, and various interesting ways of approaching it, then look at value functions, and then finally we're going to look at an actual example of how we've used this with the Army Corps of Engineers. So the basic formulation is we start off with a set of alternatives, A1 to AN, if you will, with attributes x1 to xm. And we want to form some value function of those attributes and choose the alternative for which the value is maximum. So our question is, how do we actually formulate that function such that it makes sense and serves the purpose that we intend for it? So the central issue is, what is that value function? Now what we would like to do is to come up with a value function for each attribute and then somehow compose those into an overall value function. Okay? This would be easier than having to look at the value function across all combinations of attributes. This is very similar to probability theory, where you'd like to find marginal probability density functions that are independent of each other and then compose them into an overall value probability function. Here, of course, we're dealing with value functions, but it's the same idea. We're hoping that it is separable across the component value functions. But first, before we dig into how to find this value function, let's see if we can avoid doing it. Let's see if we can figure out ways that will allow us to not go through all the math. Let's say we have a function a prime that yields attributes x prime, and another alternative a double prime that yields attributes x double prime. Assuming that all the preferences increase with x, then if xi prime is greater than or equal to xi double prime for all I, and xi prime is greater than xi double prime for some I, then you could say that x prime dominates x double prime. And hence, the a double prime alternative is a non-contender. In other words, when you're looking at two alternatives, two cars, for example, if one car dominates the other car in every attribute, there's no reason to come up with a value function, just pick the better car. So that's one way of avoiding assessing this value function that we're going to get into in a few minutes. Now let's look at another way to think about it. Let's say we only had two attributes at the moment, x1 and x2, and we plot all the alternatives in terms of x1 and x2. Let's say, for example, that might be return and that might be risk, for example. We plot all these alternatives, and the alternatives here that lie on this line, that's called the efficient frontier, or some people refer to it as the Pareto optimal set. Okay? Basically, you should always choose an alternative that is on that efficient frontier. Now, why would that be? Well, why wouldn't I pick this alternative, for example? Well, this one has the same x1, but better x2. Obviously, that dominates that. Why not pick this alternative? Well, this alternative has the same x2, but better x1. So why would I not pick this? In other words, all these ones in the interior are dominated, and so we get rid of them. We're not concerned with evaluating alternatives where they're dominated by other alternatives. So if we look at an investment context, here we have confidence, or 1 minus risk. Here we have some expected net value, and we plot all the alternatives. Okay. So let's look at a specific example. This was work I did for a large aircraft manufacturing company, and they were concerned with how to choose among the many investments they might make to improve their aircraft, improve the manufacturing of the aircraft. Some of these are very straightforward things, typical process improvement projects. For example, move left wing clip. It'll generate about $1 million of savings per year, and it's pretty sure that it'll do that. At the other extreme, we have typical technology projects where the return could be immense, but there's a lot of risk. It may not work out. And then there's projects in the middle, which are enhancement projects. So you can see we would like to actually have all these projects except for the fact that they're risky. Now, interestingly, when we use this with this aircraft company to actually make the decisions as to which ones we're going to do, there was one alternative that was right here. Okay. And they decided to invest in it. So I commented at the time, how could you invest in the worst alternative of the set? And they said, well, the customer said they wouldn't buy the aircraft otherwise. So sometimes there are other things. Sometimes it's not just return and risk. Sometimes other factors come in. And we're going to see over the course of these lectures how to take into account a wider and wider set of alternatives and attributes of those alternatives. Now here's an interesting topic that is a mouthful, lexicographical ordering. We're still trying to avoid assessing the value function. Okay? So we assume that all of these attributes are ordered by importance. In other words, x1 is more important than x2, etc. And we say basically that A prime is preferred to A double prime if x1 is greater than x1 prime is greater than x1 double prime. In other words, we only have to have the first attribute be better, and we pick that alternative. So for example, we might say price. We're going to choose the lowest price thing, period. Okay. This makes it simpler. Now you might argue that other attributes matter too, but in fact with this rule, this decision-making rule, we don't take that into account. In fact, I found this is a very useful phrase to have at cocktail parties and things like that when you're trying to make a decision and you just say, why don't we just use lexicographical ordering? Everybody's very impressed about your jargon. Beyond that, I haven't used this very often. So now let's talk about value functions. We couldn't find one alternative dominating every others. Well, lexicographical ordering was an unacceptable process, and so we've actually got to come up with a value function. So by definition, if we're indifferent between two alternatives, their value must be equal. That's the definition of indifference. The value is equal. If we prefer one to the other, then its value must be higher than the other. Okay? Again, just a definition of a value function. There are various examples. Here we have a linear value function. Here we have one that's called multilinear because it has a cross term here. And then we can have ones with power or relationships, etc. We're going to look at these two in more depth. So, what should be the form of the value function? We'd like this function of these two values, two attributes, x and y. Notice I changed notation from x1, x2 to a simpler one, xy, for this example. We'd like f to be as simple as possible, while adequately capturing the right relationship of the value of these two functions, of these two attributes. So for example, I might have job offers. I'm looking at job offers. I'm just graduating from college, and the salary varies between $50,000 and $100,000, and you can see there's some kind of diminishing return here. Okay, why would there be a diminishing return? That's because getting an increase from $50,000 to $60,000 is valued typically more than getting an increase from $90,000 to $100,000. It's both $10,000, but one is obviously a greater increase from the base. And so typically for these kinds of things, you do get a diminishing return. We also look at vacation here. So we've got a job offer with money, salary, and vacation. And you can see here we get a sort of an S-curve. Basically, a little vacation from 1 week to 2 weeks, that really feels great. That feels like a huge improvement, where from 3 weeks to 4 weeks doesn't feel as great. And one could argue also, and the reason for the S-curve is at some point it's just too much vacation. You don't know what to do with it. And obviously if you get an offer with a job that gives you 52 weeks vacation, you might question the future of that job. So what about a value function, an additive value function? What if we just add the two, maybe with some coefficients? When is that justified, to just add the two together? Well, it's justified whenever the corresponding trade-offs condition holds. What does that mean? Basically what it says here is if I'm at x1, y1, right here, and an increase of y is worth a payment of x, okay, of a in x. So I'm going to get some y and give up some x. If that's true, and then an increase of c is equivalent to giving up a here, and over here an increase of b in y is worth giving up d, then it must be here that giving an increase of c will allow a giving up d. If that answer is not d, it's not a linear function. And you can see this intuitively because, of course, you can see a symmetry here, right? A, B, B, D, D, C, C. It's all very symmetric, and that's why you get the additive property. And the additive property is nice in the sense that it makes other analyses simpler, but it could be just outright wrong. And so we've got to look at other conditions as well. So let's look at multilinear functions. Now you see what's happening here. I've got, again, Vx and Vy, but now I've got the product of the two. What does that tend to do intuitively? If I have the product, if either one of these is 0, the whole term drops out. So this is often appropriate when you actually don't want to have extremes of the variables. That's not actually reflects the preference of the decision makers. And this function holds if weak difference independence holds. So this gets a little more complicated, weak difference independence. But you can see if x1 to y1 is preferred to x1, y1, and x4, y1 is preferred to x3, y1, which would be true. I mean, by definition, those things would be true. The question of the exchange of x3, y1 for x4, y2, is it preferred to exchanging x1, y1 for x2, y1? If the answer depends on y2, then weak difference independence is not satisfied. You think about this intuitively, what it means is trade-offs among x, right? We're changing x here, x2, x4, x1, x3, right? We're trading off x. If our trade-offs about x depend on the value of y, okay, then we have to have a more complicated analysis, a more complicated model. But if, in fact, they aren't very affected by the value of y, then we get this weak difference independence, and we can get our multilinear function. So let's talk about an example. This was a project I did quite a few years ago. In fact, you're going to see over the course of these lectures that in almost every one of our models, every one of our approaches, we've got a whole variety of practical applications being used with those models. That's, I think, the best way for you to get an intuitive understanding of the value of using these approaches. So we were asked by the Army Corps of Engineers to do a trade-off analysis on the staffing levels of the Corps and their response to emergencies, to mobilize construction. So for example, with Katrina in New Orleans, after Katrina devastated that area, the Army Corps of Engineers would manage construction projects to rebuild the infrastructure. And their ability to manage those projects quickly would depend on how many staff they had to approach that. Okay. So there's a trade-off. More staff costs more budget. You have to go to Congress and convince them. But more staff means you're more responsive. Now, interestingly, they phrased this in our contract with them in terms of response time and staffing. In retrospect, it would have been better to say response time and money, because money can be used in a variety of ways. However, we were constrained to be able to do this with response time and staffing. That's what the contract said. This actually shows the benefit when you're dealing with a customer of being able to reformulate the problem, or at least understand the basis of why they formulated it the way they did. When you're constrained and can't do that, often you get stuck in a situation that is awkward in terms of the modeling. So we had 4 decision makers we worked with to apply this method, and we wanted to see what the variation was between the 4 decision makers. There were 2 generals, 2 Army generals, and 2 senior civilians. We had 1 hour to interview each of them using a booklet, coming up with the VX and VY like we showed a minute ago. And basically what we see is what they came out with was the value of time degraded with increased time. Basically, there's some point at which you're just so late, you're in the newspaper, people are complaining, etc. But the value of staffing, the budget, went down too, with a linear way, in a linear way here. The key is they would rather be able to be successful with a smaller budget because they don't have to convince the Congress to give them more budget. On the other hand, they are very concerned about response time. Okay. So we figured out the procedures we used for coming up with the constants. And just for the sake of illustration, I've averaged the constants for the 4 decision makers to get C1.9, C2.71, and the composite here of minus 0.61. Let me pause for a second and talk about why you shouldn't average these. Okay? You're trying to combine the value functions of multiple people. In the 3rd lecture, we'll talk about how to do that. The way to do it is not to average their value functions. Okay, you just can't average across their constants the way I did here, just to make the point. Okay, but the key here is that we will assess each of them individually and put them together in a more rigorous way in the 3rd lecture. But so here we have our overall value function, 0.9 times time, 0.71 times budget or staffing, and minus 0.61. What does a minus mean? The minus means these 2 attributes are complementary, or are substitutable. They're substitutable in the sense that you'd be willing to give up a little budget. You'd be willing to accept a little more budget to get a little better time, or vice versa. So there's our value function. Now let's look at what that meant. So we used those 4 value functions with their own coefficients again, not the average coefficients, and came up with 3 of the decision makers wanted to go for a much larger staff and have effectively instantaneous response time. 1 decision maker was willing to go with a smaller staff and have a response time that was significantly over a year. But don't forget, this is a year to get the full set of construction contracts in place, not a year just to act at all. Okay. Now, what happened? First of all, the 3 decision makers here, this was rather different than their intuitions, and they found it interesting that they're focused on their basic values and how those values combined produced a result that was different than they expected, and that was really interesting to them. 3 of the 4 decision makers were very interested. They like to look at how they could make decisions like this in the future using these kinds of methods. Okay. One decision maker told us to leave. This decision maker was a Army general. As we went through the process of mapping his values, he finally, in great frustration, said, "You know, young man," because I was much younger then, "you know, young man, I'm paid to make decisions, not think about them." And so he asked me to leave, along with the colonel, who was my escort. And as we were walking out the door, he said to the colonel, "Colonel, as soon as you escort Dr. Rouse out, I'd like to talk to you about this." So as we were walking down the hall to leave the building, I said to the colonel, "Wow, that was quite an experience. What do you think you're going to say to him when you get back?" And he said, "Well, I'll probably think of something creative like, 'Yes, sir.'" This man was frustrated with the way it was formulated, and I think part of it was that we were dictated that we argue in terms of response time and staffing, not response time and money. Okay? He was used to going to Congress and asking for money, not for staff. So the problem had been ill-specified. Okay? And this I want to use as a point to emphasize, you cannot totally pre-specify a problem usually. You need to interact with the stakeholders. You need to find other ways to formulate this that is more meaningful to them. Often customers will come to you, though, and they have the problem all formulated, and they want you to solve this problem. My tact is always to try to sit down with them and say, why do you think this is the solution? Why do you think about the problem this way? I'm not arguing that you shouldn't. I just want to understand. And in many cases, my experience has been, we end up reformulating the problem because of that. So let's talk about what we've done today. We've looked at the choices among alternatives where the attributes are certain. If you take a job that pays you $60,000 and you get 2 weeks vacation, that's what you get. There's no roulette wheel that's spun after you show up and your salary gets changed or your vacation gets changed. There are a lot of attributes like that. When you buy them, you get exactly what you thought you got. However, there are many choices where you don't get exactly what you thought. You get some random variation, hopefully not too far off from the mean, but you get some random variation. And to do that, we need to understand how to deal with uncertainty. And that will be the basis of our next lecture. Thanks.